What on earth is this? It's a strange circuit built with a full adder and a D flip-flop. But what on earth's going on here? The output of the D flip-flop is being looped back up into one of the inputs of the full adder. How can that possibly make any sense? Well, let's just check the syrup type of the D flip-flop. A D flip-flop takes a bit in and it gives you a bit out, but the output type is annotated with this at sign, or as we pronounce it in syrup, this is pronounced loopy. This is a loopy bit, and what it's telling you is that this bit depends only on the memory inside the flip-flop. It does not depend directly on the input. That's to say, the flip-flop already knows what it's going to send out from this output because that's already stored in its memory. It's actually what the input was last time step. And then this bit only comes out at the next time step. So correspondingly, it's okay to loop this output round further up into the component, because what's going on here is that we're using the old value stored in the flip-flop as an input to the full adder, and then the carry from the full adder is remembered by the flip-flop for the next step. So what's going on here is that we've built a ripple carry adder not in space but in time. We use the same single full adder component over and over again and a 1-bit memory to remember just the carry from one place value to the next. So we can add arbitrarily large numbers using one full adder as long as we're willing to wait. So, don't take my word for it. Let's try that in syrup by the magic of editing.
Let's code up that adder circuit. The declaration first, 2 bits enter, and 1 bit leaves. Now what's inside the box? Well, wires X and Y come in and a wire Z goes out, and then we wire up our full adder. We get a carry and a Z coming out from a full adder, and that's computed by adding the signal Q with X and Y. But where does Q come from? Well, it comes from a D flip-flop, which is fed the carry from the adder. So we can see that C depends on Q and Q depends on C. How does that make the slightest bit of sense? Well, what we're really saying here is that C depends on the old Q, but the new Q depends on C. The loop is allowed because we know that the D flip-flop's output depends only on the internal memory. So let's see if this is well defined. Great, it's properly defined. Now we should do an experiment. Let's use it to add some numbers. I don't know, let's have 37. That is 100101, so that's a 1 in the 32s and another 5. And then let's add that to 30. So 30 would be 0, 1, 1, 1, 1, 0. That's, yes, 2 times 15. And we should be expecting that out comes 67, which is 1, 0, 0, 0, 0, 1, 1. Okay, now what I have to do to make that work is I have to say experiment, and then I say adder, and then in curly braces I have to say how to initialize the memory. We need to give one bit to start with, and let's send in a carry in of 0. That's what's in the memory to start with, the carry in. And then what we do is we give a time sequence of pairs of inputs, starting with the 1s, then the 2s, then the 4s. So I turn my head to the right and I read that's 1, 0, then 0, 1, then 1, 1, then 0, 1 again, and 0, 1 again, and finally 1, 0. So I've got my time sequence of pairs of inputs separated by semicolons with the 1s, the 2s, the 4s, the 8s, the 16s, and the 32s. So let's see what happens when we run it. We get a time sequence showing what happens and what is in the memory at each time. So we can see that we get 1 and 0 with a carry of 0 gives us a 1 carry 0. And then our next 1 comes out, and then we get 1 and 1 that with carry 0, that sends a 0 out, and the carry becomes 1. And then we carry on with 1s coming out, with 1s in the carry and 0s coming out. So let's look. We have a 1 in the 1s, a 1 in the 2s, and then 0s in the 4s, the 8s, the 16s, and the 32s. And we finish with that carry of 1 in the 64s. So you can see that we're doing exactly the same business as if we were running a ripple carry adder, except that the carry is being transmitted back to the same full adder at a later time, and it's stored in the D flip-flop while we wait.